먹고 싶어서 먹었어.
출석 안 하신 분들 여기 설명 부탁드릴게요. 설명하세요.
성인아이 몇 명이나 되지? 학생들이? 아직 안 온 건가? 어? 90명?
30명 되는 거.
30명.
절반 정도 와 있어요.
shit. 2026S
Hello. Good afternoon. I'm Prof. Myung from School of Electrical Engineering. And before having a formal lecture, let me introduce myself because some of the students are not attending still. So while waiting for the students, let me introduce me briefly. So I graduated this Kaist, got a BS and MS and PhD in 92, 94, and 98 in EE department. And after getting PhD, I moved to ETLI at 3 as a senior researcher. And after that, I moved to Immersive Corporation as a CTO and R&D director. So having spent 1 year over there, Immersive Corporation is the spin-off company from ETLI. And then I moved to Samsung Advanced Institute of Technology, Samsung 종합기술원 in Korea, as a principal researcher, and I was developing some home service robot and cleaning robot. And after that, I joined the Kaist in 2008. And you can see that our lab has developed the world first robots like Zeros, jellyfish removing robot, wall climbing robot, Karos H and Paros, and Warbot, underground digging robot, and DreamWalk. This is some kind of blind locomotion control scheme for the legged robots. So we have developed such kind of robot systems. And okay, so that's the very brief introduction of me. And today, this lecture is related to AI for robot intelligence. So you will deal with the perception part and also planning part and the control parts. So nowadays, most of the robot systems utilize the ROS, Robot Operating System, as a middleware. So today I will talk about this ROS tutorial, and next week we will discuss about the SLAM. SLAM is the simultaneous localization and mapping, which is quite difficult and also quite important in the perception part. So when the robot should be operated in indoor or outdoor, we should know where the robot is, and we should know what the environment is looking like. And also we should plan the path based on the map of this environment. So the mapping and localization are the two most important parts in the robot navigation. So we will deal with that in the next week. Today we will discuss about the ROS. So what is ROS? So this is the robot operating system. It includes the libraries and tools to help software developers create robot applications quite easily. So if you understand ROS and if you are familiar with the ROS, and it is quite handy to develop robot applications. It provides hardware abstraction layer, device drivers and libraries, and also you can visualize the sensor data and also visualize the robot, and message passing. So messages are passed from application to application, so you can use this messaging. And package management. So if you develop some software, then you can pack this one in the packaging and distribute this one as a packaging and more. And this is licensed under open source license. So BSD license, Berkeley Software Distribution License. That means it is free to use, either in the academia or in the commercial applications. You can use it freely. You don't have to pay any money, even if you are developing some software based on the ROS and distribute it for your own commercial purposes. You don't have to pay money. So this is quite interesting and also That's why it was the core capabilities of the robotics developers by developing their own application based on the laws. It can be commercialized without any payment. So laws can be used as the plumbing. That means we can organize many applications currently like this way. You can manage these processes, and also they can communicate with each other. Each application can be communicated with each other. And device drivers are already available, so you can use that directly. So hardware and softwares are closely interacting because most of the drivers are already established. And tools, as a tools for simulation and visualization, and also GUI tools are provided, and also you can log the data. So as a backfile, you can store the data, all the data obtained by the sensor or the robot, and also you can replay that data later. So for debugging purposes, it is quite convenient. And some capabilities like control, planning, perception, those three parts are quite important components in the robotics. So at first you have to perceive the information, and based on that information you can plan some tasks or actions, and later you can use that information to control. So those are the three most important parts, and they are already included. And mapping, SLAM capabilities can build a map of this environment. So mapping is also included, and manipulation. If you want to have some manipulation, then libraries are already included, so you can use that for manipulation. And they provide some ecosystem, like package organization and software distribution is quite easy, and documentation. All the ROS documentations are available in ROS.org, and tutorials. There are numerous tutorials available. ROS Philosophy. It's peer-to-peer. Individual programs communicate over defined API, so you can use the ROS messages, services, and so on to communicate with each other. And distributed. Programs can be run on multiple computers, and they communicate over the network. And multilingual, you can use any type of languages like C++, Python, MATLAB, Java. And lightweight. Standalone libraries are wrapped around, so you can use it lightly. And free and open source. Most ROS software is open source and free to use. This shows the ROS history. So it started from 2007. It was developed from Stanford AI Lab as a switch yard. And then Willow Garage, this is the company. So they managed this ROS from 2008, and they distributed the first version of ROS 1.0 in 2010. After that, there are various versions like this. So you can see that the version name follows the rule like this. They use the capital letter A, B, C, D, E, F, G, and so on. So it started from box turtle and sea turtle and diamond back and so on. So they use the initials from A to Z, and in 2020, Noetic version was the last version of the ROS 1. And ROS 2 appeared in 2017. ROS 2 first released at that time. And also, the governing organization has been changed in 2013. From Willow Garage, it was changed to OSRF, Open Source Robotics Foundation. So until now, they manage all the distributions of the ROS packages. And this is cheat sheet of the ROS. So you can use this cheat sheet for having various comments, like the ROS create, ROS pack. They can be used to create the ROS packages, or they can be used to pack the packages. And also ROS core. this is the master. So you can initialize the master using ROS core. In ROS 1.0, you should first establish the ROS master. So that is done by ROS core command. And ROS message or ROS service, this will display the message or service data. And ROS run will actually run the node. Node is the executable file, and package is the package name. So this package is package name, and executable is the executable node name. For example, ROS run turtlesim node. You can see that turtlesim is the package name, and turtlesim node is the node name. So node is the final executable file. And ROS node, you can list the ROS node available and ROS info or ROS node kill. You can use that commands. And ROS launch will launch some specific node or set of nodes in the package. And ROS topic, you can see the topics, so displaying topic or publishing or subscribing the topic and so on. And ROS parameter, you can set or get the parameters using ROS param command. And ROS service, it will list and query the ROS services like this. And ROS back will record the available data and also replay the data using ROS backplay. And there are also some graphical tools, RQT graph, or some plotting capabilities, or you can display the ROS back and so on. So at first you have to install the ROS. So this is for ROS version number 1, but you will use the ROS version number 2. So later I will explain about that. For ROS version number 1, ROS version number 1 is until widely used because they are stable, and also most of the previous libraries were built based on ROS 1, not based on ROS 2. So we sometimes have to maintain this ROS 1 version. So that's why we also should learn about ROS 1. So if you are using the Linux system or Ubuntu system, then this will be the latest one, Ubuntu 18.04, what 20 version is also available. So you can just visit this website, wikiros.org. You can install the ROS melodic version, or you can automatically install the ROS using just one command. So it will bring out some shell command, row.github user content.com robotics tools master install ROS melodic.sh. This is the shell command, and you get this command, and then there will be install ROS melodic.sh shell command like this. So you have to change this mode to be executable, and then we run this shell command using bash command, and the ROS will be automatically installed using just one line. And then you have to set up the ROS environment. So you can visit this website to set up the ROS environment, or just use this one. So some aliasing and sourcing and export, that should be declared in the .bashrc file. So if you edit this bashrc, then you have to input some aliases like this. So EB is equal to nano. Nano is the editor name, so you can use any type of editor you prefer. So bashrc should be edited using EB, and SB will source this bashrc. Sourcing some bashrc means you are learning this bashrc. And then CW means change directory to the Keken workspace. Keken workspace is the main directory for ROS development. And then also CS means change directory to the Kakyoin workspace and src. This is the source directory, and you have to input some cpp file or .h file over there. So it will be very convenient. And cm will change the directory to workspace, and Kakyoin make will be performed. So you just type in cm, then this will bring you to this workspace and make everything. And then source setup bash in the Kakyoin develop, and export ghost master URI. So if you are just using your own PC as a master and also other nodes, then you just use this local host. But if you are using different IPs, then you can specify different IP here. And export those hosts to localhost. So you input those things in the .bashrc, and you have to source this one by using sb to run these commands. And there are some loss file systems, so I have made some video for this. You can watch this video.
Effectively is the software organization of the loss box. This package can contain the libraries, executables, scripts, or other softwares. And this is the package.xml, and this is called the manifest file. This is the description of the package. Your own package. This package is the software organization of the loss box. This package can contain the libraries, executables, scripts, or other softwares. And this is the package.xml, and this is called the manifest file. This is the description of the package. Some dependencies between the packages, and the meta information is stored in the package.xml. This is the virtual box. I have installed the virtual box. Inside the virtual box, I have installed the ROS. So, if you install the ROS properly, then there is the Kakyoin workspace folder. This is the main folder for programming the ROS software. So under there, you can see three folders: build, develop, and source. Under the source, you can see various sources like here, and I have installed these ROS tutorials. And under these ROS tutorials, there are some examples in here, and ROS tutorials copy being used in this example. There is the source folder. There are two source codes in here. And also, the message file is defined here, and this is the launch file to run the package. And you can see that there is the package.xml file, and if you see the details of this package.xml, you can see that this is the name, version, description, some meta information is defined here, and some dependencies of build process. We should use source CPP, standard messages, message generation, source CPP, in the build and in the running. These kind of dependencies are specified. And also, this is the configuration configuration files will compile your application. CMake list text. So in here you can see that some executable file is defined. This is the executable topic population. This is actually the execution file. And using this CPP file, you can compile and build this CPP file, and the final execution file is this one. And it shows the dependencies. And another executable file built from the source topic subscribe.cpp. This topic subscriber execution file is also this file. So we have two nodes actually. To provide content. Without
The screen is so small, so
and most consists of executable file built from the source topic subscribe.cpp. This topic subscriber execution file is also this file. So we have two nodes actually, publisher and subscribe nodes. And during this project we can create these two execution files for the nodes.
So you can create the ROS package using ROS package. So the package contains the package.xml, as we already have seen in the previous video, and also CMake list.txt. So this will provide the compilation and building rules using kicking. And you can see that each folder, each package must have its own folder. So under my package there is a cmake.list, cmake list.txt, and package.xml. And also you can see that there is a source folder, and later you can see that there is a build folder and so on, debug folder. So this shows the hierarchy of this folder structure. And we have to understand the ROS topics. So ROS topics are quite useful when you want to communicate the messages between the nodes. So master is the name service for ROS. So it will help nodes find each other. And node is an executable that uses ROS to communicate with each other. And message is the ROS data type used when subscribing or publishing on a topic. And topic, those can publish message to a topic as well as subscribe to a topic to receive some messages. So we will see the structure later in the later slide. And ROS out is the ROS equivalent of standard out, standard error. So if you just initiate this ROS core, then it will build a ROS master, and ROS out is also established, and parameter server will be also initiated. So we will use ROS core command to start the master. You also see the video. And this page has been so ROS master, it manages the communication between the nodes, and these nodes are actually the executable file. And each node registers a startup with the master, so you should start the master with a ROS core. I'll launch the ROS core at first. So I have to install the ROS
you can see is some terminals in here. So I have used the terminator terminal, and I can type in gross core here, and this gross core is executed, and this is established. Gross master has been established. And there should be some nodes. So this is the single purpose executable program, and this should be individually compiled, executed, and managed. And this is usually organized in packages. So we can run the node with this command, run, and specify the package name and the node name. And if you want to see the active node list, then you can use this loss node list. And you can retrieve some information about the node with the loss node, info, and node name. So if you run multiple nodes like this, then it is automatically registered to the loss master when it is initiated. And then these nodes will communicate over topics. So we will discuss about the concept of the topics. And those can publish or subscribe per topic. So some node can provide information using the publish function, and the other node can subscribe to this topic to get some information from other node. So typically there is one publisher and n subscribers. So we have multiple subscribers that gives the information from other publishers. And topic is the name for a stream of messages. So the messages will send out and can be received through this topic. And we can list active topics with a last topic list, and subscribe and click the contents of topic with last topic and fourth topic. And we can also show the information about the topic with the last topic, info topic.
So you can see that the topic is the channel of communication, and inside the channel there should be some data going through this channel, and that is the message.
Okay. And we can send out the messages through the topic. So this message is the data structure defining the type of the topic. It is comprised of a nested structure of the integer, float, boolean, string, etc. And also you can specify arrays of the objects, usually defined in MSG files. So let me show the details of this example in the later slide.
You can see in this slide, the .msg file contains such kind of structures like integer. This is the type of data, and number is the name of the data. So the type and data name will be specified like this in the .msg file.
And you can see the type of the topic by using last topic type and specify the topic name too. And you can publish a message per topic by using this last topic pub and specify the topic and type data. Type is actually the integer, float, boolean, and so on. And the data is the specific data you want to publish. For example, this is the example of the message file. So in the message file, you can define like this: integer, number, node, with, string, description, etc. So this will be specified in a file called .msg, and this message will be used in publishing the topic and in subscribing the topic. Okay. So we will have a very simple example. We first ran loss score previously, and I'll use the loss long, and this is the package name, total sim. This is the simulation of the total board, and total sim node. This is the actual node implementing this total simulation. And then we will teleoperate this auto using the key. So this is the node name for providing such kind of functionality. So auto teleop key will be used to manipulate the movement of this auto. And we can also graphically visualize the relationships between the nodes. So if you use RQT graph, then you can see those kind of relationship like this. So this circular one means the actual node. So there are two nodes in here, teleop turtle and turtle sim. There are two nodes, and there is one topic, or the turtle one on the bar command velocity. So this command velocity is actually the teleoperated command, teleoperated message to turtle sim. So this teleop turtle will send out this message to the turtle sim. Okay, you can see how it works. The first, I'll just copy this. Goes long, turtle sim no. To do it. So can you see this turtle here? There's the turtle appear here, and also
If you execute the
copy
node,
is
then you go here
node.
and teleoperation using your keyboard.
Use arrow keys to move the turtle.
Your keyboard input should be done in
If
this
I use
window.
the arrow key, like going forward, and it goes forward. Turning left, it turns left and going forward, and left, going forward, 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 left, forward, forward, left, forward, forward, and so on. So I can use the keyboard to command this robot at some specified command velocity. So if you want to see the topic, you can see the topic in here, show information about the topic. I can just copy and see the topic. The name of the topic here is what? Total 1 command velocity.
This is the
So
topic name.
before having that, I'll use RQT graph. So you can command like rows run RQT graph, or simply you can run RQT graph. So this is the abbreviation for this command. So I'll just call this RQT graph, and it appears that we have this topic. So I'll use this one before